Okay, late but on time. जी बेटा सॉरी जी जी बिल्कुल ट्रांसफार्मर में शामिल है. Okay जी, time lecture number 15. Today we are talking on the mechanical stresses. As I have told you previously also that whenever a transformer is working at normal load or even at full load, there are going to be some stresses on the windings, and they are windings based on the Fleming's left hand rule. Now for those who don't still remember what was Fleming's left hand rule and right hand rule, the Fleming's left hand rule was based on this assumption. If I have this both hands over here, this one was B, this one was the direction of current, this one was the force F exerted on that conductor that was placed in the magnetic field. And if this was a generator, just to give you a revision over there, the same B, I, and this was the force acted on that conductor by some mechanical prime mover over there. Now, over here, when I'm talking about mechanical stresses, there are 2 or 3 different types of mechanical stresses. The first one, which is more important, are the axial and the radial forces. Now, the 2 terms over there, they have to be first defined, that what does axial and what does radial mean over here. Now I have drawn the core-type transformer, 3-phase core-type transformer, and the central limb over here, as you can see very carefully over here. So when you are going to supposedly see this core-type transformer, I have drawn this one. This is the low voltage winding, and actually I have shifted the color over there. I could actually do this color one over there just for so let me just change that color. And
ज़्यादा टाइम से हम कोर टाइप को इस वजह से देखेंगे क्योंकि डिस्ट्रीब्यूशन के पर्सपेक्टिव से हम कोर टाइप को देख रहे हैं ज़्यादा उसके एक्सियल फोर्सेस की एनालिसिस ज़्यादा
because the current is going to be more when there is going to be a short circuit. Okay, the point is actually the short circuit current. Okay, coming back to what was axial and what was the this is actually also changed. You can do this one. Actually I missed it. So this one is the low voltage winding, certainly core distance, and this one is the high voltage winding. Now, what is axial field and what is radial field? Now, the flux which retains inside this core will not go through any other material. So that is actually the useful flux. I'm not concerned with that. But we know there is also a flux which is going to complete its path through this air gap or through the material, and that is actually a leakage flux because that is not completing its path from the iron core. So I am more interested in this flux which is inside this gap length over there, where I am actually making this one, and this field is called as axial field. Why? Because the winding axis is this one. Now radial field would be something, if I compare this one, the radial field will be something like this. Because if flux, we know flux should be flowing through over here, but some flux will be completing its path from here and here like this because the reluctance is smaller over there. So it will be having some radial flux over there. Now both of these, this is a radial field over there, similarly working over there, and this one is an axial field which is working in parallel with the winding axis over there. Okay? This is the winding over there, that's why it is called as an axial field. And when I'm talking about the radial field, radial fields are actually perpendicular over here like this, or like this perpendicular over here, or like this perpendicular to the conductor over there. That's why they are actually called as radial field, radially going out. हम याद है आपको, if you were designing the windings, the radius or the radial width over there of the winding was considered. Now both of these are going to produce 2 very different forces on the conductor, not in the normal load conditions but in the short circuit condition. Now you have done PSP, you are doing through your PSP course, and you have been told over there that whenever a generator is going to be short circuited, you are actually in the very first few transient, you are going to take the sub-transient reactance, and then you are going to calculate if it's going to be a 3-phase short circuit fault with respect to ground, then you are going to have all 3 phases short circuited. So you are going to have the sub-transient reactance, and that will be divided by the voltage, whatever it is at that point. So the current is going to be very much high, and in some cases this current will be approximately 10 to 25 times. We have seen that one. That is certainly dependent upon the impedance over there, by which it is actually short circuit. So the force that is going to be created is going to be 100 to 625 times. Now why this is over here square of the current? Now see this very carefully. Fleming's left hand rule was F is equal to ILB. F is equal to ILB. What is this current? This I current is the short circuit current over there. So if the current is now increasing to 1025 times, and what is L? L is the length of that conductor over here, and that length I have shown over here as LC, because here in this diagram, this is the length of the conductor which is actually going to experience a force over there. So this L is also constant. But what is this B? B over here is that leakage flux that is flowing through that oil duct, air duct, or through the winding. Or in other words, if I show them over here on this diagram, this BAV will be flowing in this path over there, where I have made this arrowheads over there. So it will be having this B over here. And how this B is being created? This B is being created because of the current flowing inside the winding. So B is directly related. So what this means over here, if I didn't, this B is proportional to I with some factor, of course something over there. So this means that from this relation I can easily say that force is actually proportional to I square with some factor. Certainly there is going to be some factor involved, constant of proportionality. So that's why when I am going to talk about having a current 10 to 25 times, the force is actually going to be 100 to 625 times square. Simple. Now, how these forces are going to be playing their part? Now, first of all, concentrate on this axial field, because axial field is going to be more prominent over there, because if you see very closely in radial field is just going to be a little bit here, a little bit here, maybe it's not here in this region. So axial fields are more problematic, and for one more reason which I'm just going to disclose over here. The length of the conductor here is this one. Magnetic field direction is also this one. Use your left hand rule. Okay? This is your B, this is your current I direction, this is going to be the force. Now, you know in a transformer, I have a primary winding and a secondary winding. In primary winding, if the current is flowing in the dot, from secondary winding it will be going out. So what I have shown over there, you can see, I have shown over here with this one that this direction is positive, this direction is negative. So now over here, just apply your left hand rule on this one. Current is going inward, and this is like this on the screen over there. This is current I inward, the dot over there, the cross, actually you can call it the positive current. This is B. B is going downward. If I can apply this one over here, like this. B is going downward. This is B. This is I. Cross, or you can add positive current. So force is exerted on this side. Now what is happening over here is very important. This is an axial field. And what type of force it is producing?
Outward.
Radial field, radial force.
Yes, sir.
And similarly, on the negative side, you are going to have force exerted opposite. And you can do this one with the left hand rule again. So this is going to be B. This is going to be like this. Current coming outward. Okay, going outward. So force will be exerted. So what is happening over here, that this FR over here, that is actually being produced over here by this FR is going radially out, this FR is going radially inside. So what is happening? In a short circuit one, the inner winding, which is actually the low voltage winding, is being crushing the core. The outside winding is actually being thrashed out. Now, if they both were happening in the same direction, they would cancel their effect. But now it's not happening. This inner winding is going to compress the core, and the asbestos cylinder or the insulated cylinder that we put on a stepped core to make it full circular, that is going to be crushed. And if the spacers in the winding, if it was supposedly disc winding or even some concentrated coil winding or maybe something, whatever winding, if spacers are not going to be having that much mechanical stability, the force is going to crumble it. So this is very much important that the inner winding should withstand the crushing force of a transformer. And the outside winding, which is certainly the high voltage winding, it has to be fitted with some bracing. The word used is bracing. Bracing means that you are actually going to put some metallic part, certainly not an insulator for the magnetic current, because magnetic flux we don't want in that. So you are certainly going to put something over here, put something over here, so that the winding does not go out. Otherwise, if the outside winding, the short circuit current persists for some time, the transformer is going to explode. Because the clearances which we have kept in the tank design are not that much. 40 mm, 60 mm, not more than that.
सर जो फिर जो स्पेसर्स हैं जो हम रखते हैं वो सर अगर एजेस के ऊपर होंगे सिर्फ फिर वाइंडिंग अनइवन तरीके से बाहर नहीं आएगी सेंटर से.
Exactly, this will happen. So when the second phase is going to be here, in between here, you're going to keep a spacer here also. Now these are radial forces, and how they are happening? They are happening because of the axial fields. This is very important. Axial field is producing radial forces over there. Now, if I now go on towards the radial field, now apply the very same rule. This time, the forces which you are going to get over here, if I mark them over here with again this one, use this, supposingly I'm talking about this one over here, I'm talking about this one, let's zoom in this one. B is here like this. I is coming inward over here. So the positive, if I apply this one on this one over here, this is positive going inward. This is B, so this will be actually something like over here. Like this is B like this. So this is B. This is over here. This is B. This is I. So force is exerted downward. So this one, okay, I have that one. This one. So I am going to have the force on this conductor in the downward direction. Or in practical, what is going to happen? My force exerted on this blue winding is going to make it shift downward. अब इससे क्या होगा? The spacers in between the disc winding, they are going to collapse. And on the other winding, which is actually the inner winding, it's going to have a force on the upward. ठीक है, ये डायरेक्शन ऑफ करंट पर डिपेंडेंट है. आप उसको पॉजिटिव कर दो, उसको नेगेटिव कर दो, द फोर्सेस कैन वाइस वर्सा. नाउ दे कैन नॉट इवन कैंसल ईच अदर. अब आपको अंदाजा हो रहा होगा बाय दिस एक्सियल फोर्सेस. नाउ दीज आर एक्सियल फोर्सेस बीइंग प्रोड्यूस्ड. सो हियर वी call this one as FA, we call this one as FA, certainly on the other side also, and these forces we are naming them as FR, this one also as FR. Axial produced radial forces, radial produced axial forces. Now you can understand why in the winding we kept a very good insulation over here of 9 mm in disc winding, and also in the bottom over here also. And there was a packing done so that air insulation is not there. आपको याद होगा in disc winding we did a compression of the whole disc winding because air is going to be there. Force will now then go on towards that air gap. The winding will be disrupted. And if winding, now one thing very important, maybe the short circuit does not persist for a very long time. Breaker turns on, it is protected and whatever happens. But that small millisecond or whatever time it is, the force is exerted. The air gaps are compromised. So the winding will start moving. एक दफ़ा, if it moves on from its location, it will start vibrating. In normal conditions also. Then afterward, because if a new transformer is there, you won't hear that hissing sound. Not from the corona discharges, I'm talking about the windings moving inside it. So आप अगर एक बिल्कुल नया transformer with all the resin inside it and everything over there, you're using it, you're not going to hear any magnetostriction forces that are the axial and the radial forces working over there. But after some time, you have subjected that transformer to some short circuit for maybe like 1 second, millisecond or something time, the windings will be crushed or something. So they are going to be axial forces and radial forces. जी. ये अगर मैं इसको एक सेकेंड इसको चेंज कर दूँ. दिस वन इज एक्चुअली दिस वन एंड दिस वन इज द ब्लू वन. नो सॉरी. ओके जी. नाउ
सर जो हमने ब्लू वाली जो आउटवर्ड वाइंडिंग है उसके अंदर जो करंट की कन्वेंशन ली है वो इनवर्ट्स की तरफ ली है और मैग्नेटिक फील्ड हमने ऊपर से पास को रखा. अब सर अगर हम इसको ऑरेंज के साथ स्वैप फॉर एग्जांपल,
ठीक है, नेगेटिव पॉजिटिव तो वो फोर्स ऊपर की तरफ होगी.
अंदर की एक्सियल फोर्सेस जो
हाँ
ऐसे वो दोनों की तरफ अंदर नहीं आना चाहिए
नहीं नहीं देखो आपके पास लेफ्ट हैंड रूल में क्या होता है यू हैव बी ओवर हेयर यू हैव करंट आई इफ करंट इज फ्लोइंग इन दिस डायरेक्शन फोर्स इज अप सेम बी स्टिल सेम बी अभी भी वही है करंट डायरेक्शन ऑपोजिट हो गई फोर्स अप डाउन है यानी कि कहने का मकसद ये है तो एक्सियल फोर्स की बात कर रहा हूँ यू आर अप्लाइंग दिस वन सेम ओवर दिस इज एफ ए हाउ इट इज बीइंग प्रोड्यूस्ड बी क्या है इस तरह है बी इज फ्लोइंग फ्रॉम हेयर टू हेयर और हेयर टू हेयर दिस इज बी हो गया पॉजिटिव करंट इनवर्ड ये कन्वेंशन है आप इसको उल्टा ले रहे हो छोटी अप टू यू आई एम टेकिंग दिस वन एज अ कन्वेंशन पॉजिटिव इनसाइड force is acted downward force is downward now if I take it opposite this is going to be like this one or
एक्सियल फील्ड सस्टेन करेगा एक्सियल फोर्स सस्टेन करती है सर फॉर एक्सियल फील्ड जो है एक्सियल फील्ड के लिए सर उसका फिनोमेना वो उल्टा नहीं होगा फिर एक इनवर्ट आएगी दूसरी दोनों फिर इनवर्ट की तरफ आ जाएंगे
both forces axial and radial
फील्ड के लिए पहले फोर्स की बात कर रहे थे एक्सियल फोर्स की अब एक्सियल फील्ड की बात कर रहे हैं एक्सियल फील्ड रेडियल फोर्स प्रोड्यूस जो करेगी
हाँ
वो सर अगर जो ब्लू वाली है अगर मैं उसका डॉट अंदर की तरफ ले लूँ तो उसके ऊपर अभी हम ये लगा रहे हैं
हाँ तो वो ऑपोजिट हो जाएगा वो क्रम्बल कर जाएगा एक दूसरे बिल्कुल क्रम्बल कर जाएगा वो बिल्कुल क्रम्बल कर जाएगा सो दिस कैन चेंज दिस कैन चेंज ओके हाँ कौन सा वाला ये भी लीकेज फ्लक्स है लीकेज फ्लक्स है ये भी लीकेज फ्लक्स है बिकॉज दिस इज नॉट कंप्लीटिंग इट्स पाथ थ्रू द कोर इट इज जस्ट कंप्लीटिंग इट्स पाथ थ्रू हेयर क्योंकि यहाँ क्या है देखो आपने कोर में से गुजारना है आपको कोर में से गुजारना है इट हैज़ टू ट्रेवल फ्रॉम हेयर टू हेयर टू हेयर लेकिन इट टेक्स अ स्मॉलर पाथ फ्रॉम हेयर फ्रॉम हेयर फ्रॉम हेयर और क्यों कर रहा है बिकॉज यहाँ पे आपके पास मैग्नेटिक यहाँ पे आपके पास एक वाइंडिंग और है जिसकी इसके बीच में डिस्टेंस कम है उसको लगता है कि यहाँ से परमेबिलिटी इतनी है मटेरियल की या रिलक्टेंस कम है तो इट विल फ्लो सेम थिंग हैपन हेयर लाइक दिस सेम थिंग हैपन हेयर लाइक दिस so radial fields are going to be present everyone yes their value is going to be smaller their value is going to be smaller because this axial fields they are going to flow through this one directly ye ho jayega but the radial fields which I have shown over here these will be a little smaller in magnitude as compared to the other one okay now so got your idea ke how axial forces axial field is producing radial forces radial field is producing axial forces and all because of the Fleming's left hand rule. Now coming on to how radial forces are going to be measured the formula this is a mechanical basically topic but we need to understand this so that you have an idea कि सिर्फ ट्रांसफार्मर को वाइंड कर देना is not just an art to make it withstand that 100 to 625 times of force that is important now I have taken this diagram from that same percentage X lecture, okay? And this was the Mmf waveform if you remember over there, okay? Now, if this is the Mmf waveform, so this means this is also the flux waveform. And if it is also the flux waveform, this means this is also BA waveform. Agreed? What is BA? BA is the air duct magnetic field. That is the air duct magnetic field over here in this region, over here. Now, why I require this? I require this because I know my F is equal to ILB. Now, when F is equal to ILB, I know I is going to be something 10 to whatever times over there, 25 times. L is the length, and I know that length is equal to LC over here. Height over here. Yes, window height or winding, because actually the winding is actually the important, क्योंकि उस पे force लग रही है. Window height पे नहीं लग रही, थोड़ी insulation ऊपर. Almost you can say. So now, when I'm talking about radial forces, I need a coil current, axial component of the leakage flux. Now, leakage flux has two components which I have just decided. One is axial, other one is radial. Okay? Now, I require coil current and axial component of the leakage flux. The result is the busting the outer winding and crushing the inner winding towards the core. We just did it. Now, I need to find out the flux density in the air or the oil duct. For this purpose, I know BA, you can call this as B alpha also, because A and alpha, I told you, is the oil duct dimension parameter. So if this is B alpha or BA, this is going to be equal to mu naught H. I am assuming mu naught air gap permeability. What is H? H is equal to Ni by Lc, according to Ampere's law. Now, what is N over here? The number of turns. What is current I? That is I over here. And In the denominator, I have LC. What is this? Length of the path or the winding, which means this length from this path up till here. So what I have now, I have this BA equal to mu naught IT divided by LC. And if I want to find out the average value of this B, then this means if I want to find out average value, this average value will be something here and it will be half of the maximum value which you are getting. So over here, this B average will be equal to mu naught IT divided by 2 LC over there. I have now got the B value. Now, since axial field is going to produce radial forces, so what I have done, now I have shown the cross-sectional area or cross-sectional view of your one limb. This inner one, core over here, okay, cylinder. This inner low voltage winding, then oil duct over here, and then the high voltage winding over here, like this. So you can see I have marked this one. This is the high voltage winding, the outer winding. This is the low voltage winding, inner winding over here. This is the oil or the air duct, and this is the core. Now, just like you did in your percentage X proof, we take a very small strip over there. Now, since the forces are radial, what I have done, I have taken over here a very small differential element over here, d of theta. This d of theta at an angle of theta, and now I am talking about the outer winding. I am more interested in the outer winding. Dekho, outer winding is more important because that is going to apply the force on oil. Oil पे जाएगा, वो move कर सकता है. It can move. Inner winding ने core को crush करना है. If core is mechanically homogeneous and mechanically stable thing, it won't be crushed. So the outer one is more important. So what I am taking over here, I am taking the mid value of this R. What is this R? This R is the mean radius of the outer winding. Mean radius of the outer winding. Now, बिल्कुल ठीक है. Done. डायरेक्शन बिल्कुल करंट की, हाँ. आई एम टेकिंग द वर्स्ट केस सिनारियो. ठीक है, आई एम टेकिंग द वर्स्ट केस सिनारियो कि उसमें एक तरफ बाहर जा रहा है, एक तरफ अंदर जा रहा है. अगर वो दोनों उसे कैंसिल आउट कर रहे हैं तो वो कोई मसला नहीं उसमें, अगर वो कैंसिल आउट कर जाते हैं. ठीक है, लेकिन प्रॉब्लम ये है कि करंट इज गोइंग टू बी डिफरेंट इन बोथ ऑफ द वाइंडिंग्स. ये याद रखना, current is going to be different because it is high voltage winding, the other one is low voltage winding. So there is going to be different. And F is equal to ILB. B दोनों windings के लिए same है. Assume हमने किया है कि B same है. Air duct में भी, low voltage में भी, high voltage में भी. So overall, F is equal to ILB. So I am taking the worst case scenario, that is for the outer winding that is going to bust out because of the radial forces. So now, radial forces, oh come on. आप ये डिसाइड नहीं कर सकते, एक सेकेंड, आप ये डिसाइड नहीं कर सकते बिकॉज दिस इज AC, दिस इज अल्टरनेटिंग करंट. अगर एक वक्त में डायरेक्शन अंदर है तो एक वक्त में बाहर है. ये इट्स नॉट DC नहीं है. इसलिए मैंने ये जो पॉजिटिव और नेगेटिव वाली बात की थी, ये सिर्फ एट वन इंस्टेंटेनियस पॉइंट, यानी कि बेसिकली आई वॉज हैविंग साइन वेव एंड आई वॉज समथिंग हेयर विद पॉजिटिव एंड नेगेटिव. मैं पॉजिटिव में, अब मैं नेगेटिव साइकिल में आऊँगा तो वो उल्टा हो जाएगा. अब ये डिपेंड करता है कि आपका फॉल्ट किस पॉइंट पे आया, इन द पॉजिटिव साइकिल और द नेगेटिव साइकिल. ये बहुत इंपॉर्टेंट है. देयर इज इक्वल चांस. ये आपके ऊपर डिपेंडेंट नहीं है कि आपका फॉल्ट है. कौवे ने जाके उसी टाइम पे मरना था जब पॉजिटिव साइकिल था या नेगेटिव साइकिल था. दैट टोटली डिपेंड्स अपॉन योर चांस ऑफ प्रोबेबिलिटी. सो यू हैव टू टेक द वर्स्ट केस सिनेरियो. ओके जी, कमिंग ऑन टू ओवर हियर. रेडियल फोर्स एक्टिंग ऑन अ स्ट्रिप situated at a mean radius R with an angle d theta of the coil. So I am taking this small radius or strip over there. Angle is d theta. What will be dFR equal to? That is the force exerted on this strip. F is equal to ILB. So what is I? Current. Length of the strip. What is length of the strip over there? The length of the strip will be equal to, if you remember, we know from mathematics, S is equal to R theta. What is R? Radius of mean radius. And what is theta? D theta. So over here you can see very carefully what is the length of the strip. It has been replaced by R d theta. Flux density, we already know this value from the previous slide. So I have BAV into I into R d theta and I'm multiplying it by T because there are number of turns over there. जैसा से आप machines के अंदर आपको एक coil के अंदर एक turn है तो उसको आपको force पता चलता है. You multiply it by how many number of turns you have inside that coil. So you are multiplying it by T to find out the total. So this DFR is going to be equal to mu naught IT divided by over here 2LC multiplied by, I am putting this formula over here. So this is I into R d theta T. So now my DFR becomes equal to mu naught divided by T, IT square. You can change it to N over there because this one is taking N, this one is taking T. So it's totally up to you. R divided by LC d theta. Now I have to integrate this DFR from 0 to 360 or since this is going to be in radians 2 pi. So overall, when I am going to I am going to integrate it from 0 to 2 pi. I am going to get mu naught divided by T and in place of this R, I am going to multiply it by 2 pi R. And what is 2 pi R? Since R is the mean over there, so 2 pi R is going to be equal to LMT, mean length of the turn. That is the outer winding. So FR is now equal to, if you see this formula, this is equal to mu naught divided by T, IT or TI square into LMT divided by LC. So what component is important over here? You are getting over here mu naught constant, 2 constant, LMT and LC also constant. But if you have large amount of current, it is being squared. So current jitna zyada hoga, force is going to be doubled, squared over there. That's why current, if supposedly short circuit current is 10 times, the force will be 100 times. If it is 25 times, it will be 625 times. That's why, I don't know you have reached up till that point or not, but whenever you are designing a 3-level protection, step protection, पढ़ लिया आप लोगों ने अभी तक नहीं पढ़ी, 3-step protection. I guess after mid it will be coming on. Whenever you have that 3-step protection for a generator or a transformer with a generator, you always keep the first relay that has to trip in half of the cycle, which means 20 to 15 millisecond के अंदर आपको उसको trip करना है. What I mean by this, we know whenever supposedly the fault occurred at this point, at the peak, what happened? The current will go to extreme value and then come down and then you will have some that decaying potential over there, okay? Depending upon whatever. Now, when I have this one over there, you have to cut it off at the peak or even before the peak so that it dies down. Because if that current reaches the peak value, the transformer is gone. Transformer is certainly gone. You can't even brace itself for safety. So this FR over here is very, very important and that is dependent upon this current I over here, that is over here. Now, just a little option over there, since I over here may reach symmetrical peak, that is the short circuit current from your PSP, you all know symmetrical and unsymmetrical components, I'm not going into that detail. And I can write this I, since this I is RMS, this I is RMS, so I can write in terms of time t, under root 2 means multiplied by 1.414 peak ban jayega. So RMS multiplied by peak under root 2i sine omega t plus t, making it a sine wave function. This is the RMS value I. So when I will square it, now see this very carefully, when I will square it, this 2 will be now 2i square into sine square omega t plus minus phi. And this I square t, I want to find out its average value. The average value will be I square. Okay? You have done this one in your power electronics course also. So I don't need to do. आपके पास एक sine wave है, उसको आप square करते हो, उसकी average value is going to be equal to RMS value of square over here. ठीक है जी? So got it? So what this means, if this was FR, this FR was equal to this formula. Now if I want to find out the average value is the same and this I is the same RMS value over here. Got it, Svanti? So why I am interested in the average value? I need to find out the peak also, but I need to find out the average value so that the winding can be designed based on that average value also. So this is my FR average. This is equal to mu naught by T, Ti square into LMT divided by LC. The axial forces now, you have this axial forces and you know axial forces, you can control them by having sandwich winding. Sandwich winding is used in shell type transformer. So how you are actually going to control it, this is the shell type transformer shown over here, and in this shell type transformer very easily I have drawn this one, and now if I take this portion of the winding, okay ji, and I have drawn this winding over here. Now see this very carefully how this is done. This is MMF waveform again. What they have done, this is certainly the low voltage winding because towards the core, this is also low voltage, this is high voltage, this is low voltage, this is high voltage. Certainly, when I am going to measure this length would be the window height, something minus over there. Now, why I have bundled them? कोई मुझे बताएगा what's the advantage of bundling them? If you see, मैंने आपके पास अभी पिछले diagram के अंदर, I had one, then next, another one, another next, another one, another next, and then one. Now over here, I have made it in form of bundling, which means these are the high voltage, this is also high voltage, this is also high voltage, this is high voltage, this is low voltage, and all low voltage. Now, advantage is this, that you are actually cancelling the inner ones over there. How? If you see very over there, this one, whatever flux this produces will be cancelled by this one. Then certainly it will be cancelled by this one, the next one. The only things which are going to remain are going to be these last two ones over there. Now, I don't know how many of you gone through that assignment number 4C I gave you for percentage X. In that one, I told you that in shell type transformer, I am going to have how many N type of bundles over there. This is one bundle, second bundle, third bundle, and then certainly 4, 5, 6. And these are half bundles on the outer side. Now the MMF waveform, coming on to this one. Now you see over there, this air gap is there, this air gap is also there, this is also there, this is also there. Now if this is low voltage, this is low voltage, this is taking it down, then it stays straight because there is an air gap, and then this is 2, 3 high voltage. So this will increase it up till the maximum because same current is flowing. Turns different हो सकते हैं, current same है क्योंकि सारे series में. Then straight and then coming down towards the negative because it's the low voltage winding, and then straight and then going up again and then over here and then coming down over there. Now if you see very closely over there, this one cancelling this one cancelling this one, so you only need to now have this one and this one, you are actually going to balance out them. So what this means over there, that the forces on this type of shell type transformer sandwich winding, you only have to take into this and this one because they are actually going to be not cancelling their effect. So now what is this WC? This WC is the width of your winding over there. And why I am talking about this one? Because I am talking about axial forces. Axial forces in this winding will be in what direction? जी कोई बताएगा मुझे? ये winding का flux ऐसे आ रहा है. This is over here, this is over here, this is over here, similarly over here, similarly over here, like this. So what is this WC? Is the length of the flux path. What was this used for? If you remember, what was B? B was equal to mu naught H. And in H you replaced it by Ni divided by Lc. So instead of Lc you are going to put Wc. Okay? So your B over here is going to be written as half mu naught ITN divided by Wc. And how we have taken it half because for the half value, average value over there. So this BAV is going to be equal to half mu naught ITN divided by omega C. WC, and Tn over here is the number of turns on each end of the half coil. Number of turns on each end of the half coil. So now if I need to find out FA, I'm not going to go in that whole proof over there. That can be done very easily because we know what is B, what is all that. So what is B is this formula over here, current I. Then I have the length LMT over here, the length of the winding, length of the mean turn, and multiplied it by Tn. What is Tn over there? जी कोई बताएगा मुझे? Number of turns in one half segment. आपके पास ये पूरी winding थी, इसके अंदर आपके पास n number of segments हैं. You have n number of segments over there. This is 1, this is 2, this is 3, and certainly this is 4, and this is also 4. So you are dividing it by n. This gives you the number of winding, and you are dividing it by half. Because half of this is here, half of this is here. ठीक है? So you had n segments. अब ये यहाँ मैंने ये एक segment है, ये एक segment है, ये एक segment है. ये n number भी हो सकता है. So you are dividing the total number of turns by n over there, and then you are dividing it by 2 to find out this one and this one. हाँ वो लो वोल्टेज, मैं अभी सॉरी हाँ यहाँ पे कैंसलिंग इसकी होगी, मैं इसकी करूँगा n segment. So n segments on the low voltage side, n segments on the high voltage side. So since I have low voltage over here, I have to first of all find their force. So over here you can see over there what I have done. This is mu naught I Tn divided by omega c, same thing coming on over there, I Tn over there multiplied by LMT, and as I told you Tn is equal to T by 2n, where 2n is the number of total half coils. Okay, so it will be depending upon whatever is over there. So now this FA is written as, now instead of this Tn you put T by 2n. So you can see what is happening. 2n, you square it over there, and then you have already 2 over there, so 2 multiplied by 4, you got 8 over there. Then you have n square over there, it square LMT divided. This formula is approximately almost same just like this one. The only thing is this, that in the denominator you have 8 and n square. So the force is inversely proportional to 8, a constant figure, and then n square. So आप जितने segments ज़्यादा बनाएंगे, आपके आखिरी दो and half coils जो हैं, उनमें number of turns कम आएंगे. So you will be having less force to handle over there. Of course. So आपका n कम हो रहा है, so that's why these two are going to have less force as depicted by over here 8n square it square over there. So these are axial forces, and axial forces for co-type transformer. कोई मुझे बताएगा उसके लिए क्या होगा? This is a shell type transformer. हमें बड़ा आसानी से पता चल गया जी ये axial forces को तो हम shell type में बड़ी आसानी से control कर सकते हैं. What about the transformer that is co-type? I am talking about this case over here in this one. जी, what will happen? Now if the window height is adequate, no issues over there, and if they both are symmetrical, आपको याद होगा हम अभी तक जितने भी डिज़ाइन किया है, distribution, power transformer, whatever, there was a limitation every time कि जी your transformer windings both one should be equal length. If they are not equal length, the problem will occur. Why? Because then it will be having a different force over there. It can move then. The whole winding can move then. So the case would be something like this. If I show you over here on this diagram, so this will be the forces due to asymmetrical winding types. I have shown you over here 3 different types. First one, low voltage again, high voltage over there. Mmf waveform would be going up because here in this region there is nothing. So this low voltage is increasing the MMF, and then afterwards there is high voltage over there. So this is cancelling over here like this. Then if you see this one, you arrange it in the center. When you arrange it in the center, the MMF waveform something becomes like this. Now this is still acceptable. Why? Because in this region, if I show this one, this region, the MMFs are being cancelled somehow. Okay? This region and this region, there will be a problem again over there. So this or this is a little better as compared to the first one. And if I have something like this, now you have some distances over there. Now the advantage is this, because these are axial forces over there, they are trying to move up. हमने पहली winding को ऊपर कर दिया. They are not going down. So these MMFs are still cancelling each other. But whenever there is going to be unsymmetrical windings, they are going to be a problem over there in the event. That's why as a designer, it's your utmost responsibility to have the low voltage and the high voltage winding as equal as possible. And in distribution transformer, this problem is even more severe. Why? Because in distribution transformer, you are coming on from 11 kV to 400 volts. The current is huge, 630 amperes, 500 amperes. ये करंट आपको वहाँ नहीं मिलेगा in a generating station transformer or a transmission line transformer, because here the current is being squared. So distribution transformer के ऊपर ये forces ज़्यादा problematic है, because the current value is large over there, because you are going on up to the level of 400 volt or 230 volts over there. Now there is a proof linked with this one. See this one. I'm going to ask you to actually give me the answer. Of course, वो फिर नीचे की तरफ आएंगे, अंदर की तरफ आएंगे, वो of course, because the problem will be in this worst case scenario. That's why I have taken it over here. हाँ सबसे लेफ्ट वाला वो बिल्कुल ऊपर की तरफ है उसमें. Okay, I have worst case scenario. I'm taking the worst case scenario over there. You have B1 as the thickness of the LT winding or low voltage. B2 is the thickness of the other one. And certainly when you are going to complete this transformer, this is the central limb. So there will be a low voltage winding on this side. And then certainly there will be a high voltage on this side. So this distance is X. Then this distance over here is also X over there. And the other winding which will be drawn in the same window over here like this, over here. Eh? Sorry, yes. It will be, let me draw it actually. So, in fact, let me copy this one. Actually, मैं ये थोड़ा सा वही मैं So if I have it over here, okay. And I have this one as copy as something like this, and I have this one over here for the other winding. So you have something like this. Okay, so I hope you have got this one, and this one is certainly over here. This one is actually white. I should be making it a white over there. So this one is that B1. This one is that B2. And certainly this oil duct is there, but I'm assuming it's negligible over the size is very small. So I'm not taking that into account. Now, tell me how this works. You have a radial field. It will interact with the winding currents to produce axial forces. That's the order. Now, they are suggesting that in this window height or window width over there, since the windings are unsymmetrical, the forces are acting or trying to move it up or down, whatever that force may be. So this distance from this one is X. This distance from this one is going to be equal to 2X. Approximately, okay? A little bit addition over there, because we know A, we know B1, we know B2, okay? So this 2x is equal to this one. Tell me how this B is equal to mu naught K IT divided by 2x. What is K? K over here is this distance over here, over here. ये IT होगा, क्योंकि आपके पास MMF कितना होगा उसके अंदर, किसी भी वाइंडिंग के अंदर I1 N1 है, दूसरी वाली में I2 N2 है. So just giving it a common name IT or IN, and it will be some K factor. K factor will be something, point something, 0.8, 0.9 or whatever, depending upon how much you are actually increasing it over there. Question over here, answer me why this B is equal to mu naught K IT divided by 2x. G. This is a core type transformer, not shell type transformer. The problem here is for axial forces I am talking about. So this is 2x. By B के लिए क्या करते हैं? B is equal to mu naught H. H is equal to Ni divided by LC. This is LC, the mean length for the flux, because when I am going to complete this flux is going to flow and then complete its path over here like this. It's going to complete its path over here like this. So this is the distance traveled from one limb to the other. And this problem is more problematic. That's why we are discussing it, because there is an unsymmetry between the winding lengths over there. So that's why this is 2x. You want to find out the average value, this will be half over there, because depending upon the whatever value. So this is called as the cross flux density, because this is crossing the whole window width over there. So now you find out FA, axial forces over there. Same thing, add this B over there. LMT, what is LMT? LMT is the length of the mean turn over there, and then I am multiplying it by IT over there, and you just take this equation and then you can write down, instead of X, you can write down A plus B1 plus B2. So you have now axial forces for unsymmetrical winding, which means you have something, a distance over here that is not covered. So the windings are uncovered, and based on this one, this is your average value. I have how this average value is done based on the same assumption. If current is RMS, you square it, the RMS value is still I square. Okay, average value. So same assumption over there, this is your average value. Now in this one, you can see very easily over there, this factor is additional. अगर आपने unsymmetrical winding रखनी है, you increase this window width, आपके forces controlled होंगे, because cross flux not going to flow. Problem cross flux है, लेकिन आप जब ट्रांसफार्मर का this 2x बढ़ा देते हो, तो आपकी कॉस्ट बढ़ेगी, आपका योक की लेंथ बढ़ेगी, आपके कोर की रिलक्टेंस बढ़ेगी, ऑयल टैंक का साइज बढ़ जाएगा. So all these, of course, core losses बढ़ जाएंगे. So this is a trade-off again every time. ये problem, these formulas are being used by mechanical, but still, since they directly affect your case also. So this is very important that you take into consideration what is your FA or what is your FR on your transformer whenever there is a stress going on. Okay, I will just go through this very fast. This is a very small example. I want to just do it over there. Effect of frequency variation. We already know this one. These are formulas. No need to prove these two formulas. One is the eddy current loss. Other one is the hysteresis loss over there. This X is dependent upon the material property. If anyone can find out a proof of these two, please do share with me. I have been trying to find out these proofs. These are actually empirical proofs coming on, and they are not done even in this book. But you have been using these formulas in your machines course also. ये आपको वहाँ पढ़ाए गए थे in Fitzgerald. This formula was written. K is the constant again here for the eddy current losses, and KH is depending upon the hysteresis losses or the material. And this BMX, so X is actually either 1.6 or 2.2, but normally this X is taken as 2 if the material is normally okay. So do solve example number 7.17, solved example from R.K. Agarwal. This is very much important. There is a small proof linked with it, and it's telling you that if you change your frequency, what will happen to hysteresis losses and eddy current losses? So do solve this 7.17 example over there. And if I just solve this example over here, this is example number 7.16. Let me just solve it over there. It's a 500 kVA transformer. It's an 11,000/440 volt delta /Y. High voltage turns are given 1660, and LMT is given as, what is LMT? The mean circumference over there, 93 centimeter. High voltage के ऊपर हमने force निकालनी है. We need to find out the radial force that is exerting on this transformer high voltage winding. Now we know the formula. Let me just copy that formula over here. That FR was equal to, let me just kind it out. This is that formula, and if I need to find out the average formula, so this is my formula over here. So I have this one over here like this, and so this is my formula over here. And for this one, what I need, I require over here, जी क्या चाहिए मुझे इसके लिए? I require LMT, I already have it. I require LC. We still don't know what is the current I. ठीक है जी, current I हमें नहीं पता. हाँ, we have it over there. Since it's the high voltage winding, it's connected in delta. So I of H will be equal to 500 kVA, which means 10 raised to power 3, and this is connected in delta. So line and phase voltage. ये गलती please मत करना. You are in final year. In your exam, I saw one paper quiz मैंने देखा था, उसमें उसने गलती की हुई है. कौन सा student है मुझे नहीं पता. एक second, just let me write it down. 3 into 11,000. जी कितना है? 15.15. So please, whenever you are doing this, is the first very most important step to find it out. Okay, now I have to find out the short circuit current, and it has been told that this is equal to 20 times the rated current. So this will be 20 times multiplied by 15.15, 303.03 amperes. So now if I want to find out the radial force average, certainly this will be equal to mu naught is equal to 4 pi into 10 raised to power minus 7 divided by 2 multiplied by, what is the number of turns? Already told to us, 1660 multiplied by I, 303.03 square, certainly multiplied by LMT. One thing very important, this is force in newtons. So you have to convert this one into meters. So this is 0.93 meters LMT. So you first of all, remember in exam or anywhere, if you are having the habit of always using the SI units, whenever you solve an exam, solve a numerical in any exam, whenever you write down the data, उस data के साथ please convert it into SI units. Otherwise, if you think you will convert it on the very end, you will do a mistake. आपका पूरा, क्योंकि दिस डिज़ाइन इज डिपेंडिंग अपॉन द फर्स्ट वैल्यू. अगर आपने पहली वैल्यू गलत निकाल दी, the whole design is lost. So you'll only be getting the marks of your formulas or whatever. And one thing very important, as I've told you, since I'm going to give you a lot amount of time, please write down the formulas or any explanation. Like why you are taking 2W by 1D, why you are taking 1W by 2D. Write down the explanation. So I know, even if your mathematics are a little bit wrong, I know what you have done. Okay? So just don't go at a very fast pace over there. So this is 0.52 meters and this is 0.52 meters. Ji Hamza, what is the value? FRAV. It should be, I'm writing down from the book, 284, 289, 284, 284 again. 345.85 newtons. Acha. Now, mechanical engineers, they don't like values in newtons. आपने अक्सर देखा होगा, they always, not pounds, and we're not in British, we always require in tons. Okay, how many tons it can have it. Now, how to convert a Newton force into ton? Newton force कहाँ से आ रहा है, किस फार्मूले से? F is equal to ma. A is the gravitational acceleration, G 9.8. So now you want to first of all convert it into kilograms. So this FR, if you want to find out in kilograms, first of all thing 284,345.85 divided by 9.8 over there. And now having it in kilograms, you want to convert it into tons. 1,000? 1,000, yes, certainly 1,000. 28.985 tons. टन्स के स्पेलिंग प्लीज़ TONNES करना, टी ना लिख देना, टेस्ला बन जाएगा वो. ठीक है. सो दिस इज़ योर फोर्स एक्सर्टेड. कितने KVA का ट्रांसफार्मर है? 500 KVA एंड अ शॉर्ट सर्किट. द फोर्स इज 28.985. दैट्स व्हाई यू सेड whenever there is a distribution transformer working and if it is working at full load or by chance it's raining or something and there is a short circuit fault, please don't go near it because it's going to be exploding it. अब वो इतनी फोर्स के साथ अगर हाई वोल्टेज वाइंडिंग एक्सप्लोड करेगी तो यू कैन इमेजिन दी टैंक और वट एवर ऑयल इट्स गोइंग टू गो ऑफ अप टू लाइक 200-300 मीटर्स वेरी इजीली ओवर देयर. ठीक है जी. सो दिस इज़ योर टुडेज लेक्चर एंड होपफुली प्लीज़ काइंडली गो थ्रू वन थिंग वेरी इंपॉर्टेंट. हाँ, कल प्लीज़ यू हैव टू सबमिट मी ऑल दी असाइनमेंट्स. हाँ मैं लिख रहा हूँ, मैं वो भी लिख रहा हूँ. एक सेकेंड. वन थिंग आई हैव नॉट डन इन दिस पार्ट, but I guess you have done your machines course, so that is not very much required, but that is the efficiency calculations and the regulations. This is your efficiency calculations over there. You already know how efficiency is calculated. You need to find out output divided by input and at your power factors whatever. ये हमने calculations machines course में की हुई हैं सारी at different efficiencies or whatever. Please kindly go through this one. ठीक है. एनी क्वेश्चंस कैन बी आस्क्ड ऑन दिस वन. एंड रेगुलेशन, वोल्टेज रेगुलेशन फार्मूला, बिकॉज आपने एक ट्रांसफार्मर डिज़ाइन कर दिया, उसका परसेंटेज X परसेंटेज R निकाल लिया, तो आप उसकी रेगुलेशन निकाल सकते हैं. एंड इन योर बुक दे हैव फाइंड आउट एट यूनिटी पावर फैक्टर एंड एट 0.8 पावर फैक्टर. सो ये 2-3 फार्मूलाज हैं. प्लीज़ काइंडली गो थ्रू दैम. जस्ट अ रिपीटिशन ऑफ व्हाट यू हैव ऑलरेडी डन इन योर मशीन्स कोर्स ओवर देयर. So this is all for the mid chapter number 7 from the R.K. Agarwal and chapter number 4, 5, I guess. Just like quiz, nothing special.